So we talked about precipitation reactions. Another type of reaction, two types really, acid-base and gas evolution reaction. So these are classes of reactions. And both of these are reactions, they have a similarity to the precipitation reactions in that they arise from an ion of one substance, ionic compound, reacting with an ion from another substance. So the acid-base reaction, it is also called a neutralization reaction, so you need to recognize both of those terms. This happens when you get an acid reacting with a base, and they neutralize each other. So hence the name acid-base or neutralization reaction. When you have an acid and a base that react together, you get water, and oftentimes a salt, meaning an ionic compound. A gas evolution reaction is going to evolve a gas. You're going to produce a gas. Usually we observe that as bubbling or fizzing. So like when you put an Alka-Seltzer tablet in water, or when you put some vinegar on baking soda, you see this fizzing, right? That's a gas evolution reaction. It's producing a gas. So we need to learn a little more about acids. I just want to make sure I'm in the same section. So different definitions. Arrhenius definition is that an acid is any substance that produces hydrogen ion in an aqueous solution. So this definition is a little more general and more inclusive than our nomenclature definition of it starting with an H. Okay. So an example, HCl, hydrogen chloride, we could name it if it was a gas, but when we put it in water, it forms hydrogen ions. Therefore, it's an acid. What really happens, though, with these acids, let's think about what is a hydrogen ion. How many protons does a hydrogen have? One. One proton. How many electrons? One. So you got one proton, one electron. To form an H plus ion, it has to lose its electron, and what's left? A proton. Okay, so we got a proton out by himself. A hydrogen ion is like a 3-month-old baby. Do you send them outside to play by themselves? No. No, they're too small. They need to be carried by someone, right? That's how I think of these hydrogen ions. So a hydrogen ion is really just a proton, H plus. And so what really happens is the hydrogen ion is not happy by himself, and there's lots of water molecules around, and so he rides piggyback on a water molecule. The water molecule is holding this hydrogen ion, making him feel more comfortable. Okay? So what do you get when you put those two together? You get H3O plus. This is the hydronium ion. There's this name, hydronium ion. And this is what actually occurs in an aqueous solution. You do not have free hydrogen ions wandering about any more than you see 3-month-old babies going on rides by themselves at Disneyland, right? It just doesn't happen. Where do you see 3-month-old babies at Disneyland? You see them in a stroller or in somebody's arms, right? And it's the same thing with hydrogen ions. Now, most chemists use H plus and H3O plus interchangeably. And unfortunately, this can cause confusion for students. But writing H3O plus all the time makes some of our equations a bit unwieldy, and it gets tedious. And so I just want you to understand that even though we may be using H plus in our equations, we understand implicitly that there is a water molecule that is carrying this guy around. Okay? So that's an acid. A base, under the Arrhenius definition, is a substance that produces hydroxide ions in solution. Something like sodium hydroxide. Sodium hydroxide is a soluble metal hydroxide. It will dissociate into sodium ions and hydroxide ions. There are other bases. Ammonia is also a base. And you may say, well, gosh, how does that produce hydroxide ions? Well, it does so by pulling hydrogen ions off of water molecules, leaving hydroxide ions behind. For most of these acid-base reactions, though, we can recognize the bases as some metal and hydroxide. We have polyprotic acids. And again, it's helpful to understand prefixes and roots of words. So poly is a prefix meaning what? Many. Protic refers to proton. The hydrogen ion is a proton. So a polyprotic acid is one that has more than one acidic hydrogen ion on it. So they contain more than one ionizable proton or hydrogen, and they release them sequentially. So sulfuric acid, you can recognize polyprotic acids because instead of just an H up here, they're going to have H2 or even H3. Both of these hydrogens are acidic. When you put sulfuric acid, H2SO4 in water, first it loses one hydrogen, and then it loses the other one. Interesting, sulfuric acid is strong in its first ionizable proton, but weak in its second. So basically what happens is you've got the H2SO4 aqueous, and first it loses one of its protons to form that hydrogen sulfate ion. This has a -1. And then that one is a weak acid, but it can go to hydrogen ion and sulfate. And I don't expect you to be able to do that equation right now. I just want you to have an idea of how that works. Some bases also produce more than one hydroxide ion per mole of base. So if you had, let's see, which of those are soluble? Barium hydroxide, maybe? Off the top of my head, I can't remember if this is soluble in water. But this guy would produce 2 moles of hydroxide ion for every mole of base.
Is there a name?
No. There should be a name, shouldn't there? We have polyprotic acids. Why don't we have multi-hydroxy bases? I don't know. There's no name for that. None that I know of. So what happens in an acid-base reaction, remember, an acid produces a hydrogen ion, a base produces a hydroxide ion. Well, the hydrogen ion from the acid combines with hydroxide ion from the base to make water. So we can see that down here. H plus OH minus. If you're not thinking about how that would actually happen or anything, just, well, what if you put these two things together? Well, you've got a positive charge and a negative charge, so the charges would cancel out. So what we end up with here has no charge. And now we've got a total of 2 H's and 1 O, and so that's water. So here's the molecular equation. Here's hydrochloric acid. This is going to ionize and release its hydrogen ion. Here we've got sodium hydroxide, which will dissociate and give this hydroxide ion. And so these two are going to get together and be water, and what's left will be the sodium and the chloride. So usually what happens is we get water and salt. Not necessarily sodium chloride, but an ionic compound. And I have a great picture. It should be in the slides, but I'll have to show it to you separately. We can think of these in the same way that we thought of the precipitation reactions, thinking of them as swapping partners. Because what's going on here? This positive ion from the acid is getting together with the negative ion from the base. The difference is this isn't an ionic compound, it's a water molecule. But what's left is the sodium ion and the chloride ion. So again, we have that same idea of these two couples coming to a party and swapping partners. There's an illustration. I don't feel like talking about that. Here's some common acids and bases. We've encountered many of these in our study of nomenclature. This is where we get our list. Okay, hydrochloric, hydrobromic, hydroiodic, nitric, sulfuric, perchloric. These are the strong acids. Those guys are the strong acids. Acetic acid and hydrofluoric acid are also pretty common. Those are weak acids. Anything that's not in this list, any acid not in the list, is a weak acid. Here's some common bases. You've got sodium hydroxide. They're all metal hydroxides, calcium hydroxide, barium hydroxide. And ammonia is also a common base, even though it doesn't have hydroxide in it. Because what ammonia does is shown down here. Ammonia will take the hydrogen ion from a water molecule and become an ammonium ion and leave hydroxide. So it produces hydroxide. Question?
The strong acids are labeled as strong because the ion is completely in water.
Right.
Does it have anything to do with their properties at all? Or are they only called strong because of their complete ionization?
Does the fact that they're strong have anything to do with their properties? Not in the way I think you're talking about. When we say strong acid, that makes it sound like that acid is like more reactive and more dangerous, right, than a weak acid. Oh, it's just a weak acid. That's not going to hurt you. There's no real correlation between weak acid, strong acid, dangerous acid, safe acid. That has more to do with concentration. So you could have a strong acid solution that wouldn't hurt you at all and a weak acid solution that would burn your skin off. Okay? So, good point. Strong just means it ionizes completely. So, let's write molecular and anionic equations for these two guys. Woohoo! So, we're going to approach these just like we approached the precipitation reactions swapping partners. So HCl is H plus and Cl minus, and barium hydroxide is Ba2 plus and OH minus. And if we change partners, we're going to end up with H plus paired up with OH minus and barium paired with chloride. So when you shove these two together, you may just, plus minus, I'm not thinking very much, HOH. You look at that, and that looks weird. Yeah, it looks weird. That's H2O. What's the state of water? Liquid. Unless specified otherwise, when we have state symbols here, assume room temperature, normal atmospheric pressure. So barium and chloride are going to go together in a way that would be barium and chloride. Would that be an aqueous solution? Solubility rules. Those halides are generally soluble except silver 1, silver, mercury 1, lead 2. Not one of the exceptions. This one's soluble, so we put aqueous. And then we have to balance this. I look over on the right side and I see I have 2 chlorides. So I want to put a little 2 in here. And this is one of those bases whose group doesn't have a name, that it gives off more than one. We're going to need 2 water molecules to account for the two oxygens here. And then that should take care of the balancing. Oops. So we wrote the molecular equation. For the net ionic equation, we need to look at what's changing. Well, we already have the ions written down here, right? Or just our little scribblings. So there was hydrogen and chloride and barium and hydroxide, and they were making these guys over here. So we can kind of take some shortcuts here. This is a strong acid, so that would be written as ions. This is a soluble ionic compound, that would be written as ions. This is a liquid. Is that going to get written as ions in a complete ionic or even a net ionic equation? No. So I'm going to fix this guy, H2O, because that's a liquid. Barium chloride, soluble ionic compound, that would be ions, right? So then this is not balanced, this is just our little sketchy work we're kind of scribbling. Are there any things that appear the same on both sides? The barium and the chloride, right? So over here we have a barium, and there we've got a barium. Those are spectators. Over here we have a chloride and a chloride. And what's left? That's what the net ionic equation is. What's left is a hydrogen ion and a hydroxide ion making water. This is the net ionic equation for all acid-base reactions in aqueous solution. So did we even have to do all that stuff? No, not really. Now we don't have to do it on the second one. Let's try to be maybe a little more sophisticated on the second one and not write all this junk out. So what I do, and what you can do as you get better at this, is you can do this stuff that I've been writing out here mentally on a whiteboard in your brain. So I'm looking at this and I'm saying, okay, I've got hydrogen ion and sulfate ion, and I've got lithium ion and hydroxide ion. I'm going to swap partners. The hydrogen and the hydroxide are going to make water. So I'm going to get H2O. And then I'm thinking about the other ions, lithium and sulfate. Lithium has a +1 charge. Sulfate has a -2 charge. So this is going to be Li2SO4. Is that soluble? Yes, it is. Lithium compounds are soluble. Squeeze it in. So you don't have to write the stuff down if you're coming up with the right answers. If you're not coming up with the right answers, then at least at the beginning, you need to write everything down, right? All the steps, all the charges, so until you can see it without writing it down. Is this balanced? No. There's 1 lithium here and 2 over there. So that tells me I need to stick a 2 in here. And the sulfates are okay, but I need more waters. So I'll put a molecule. Balancing equations is a pretty big deal. I know we're covering everything in here really, really fast. You gotta just keep up. And if you start to fall behind, you need to ask for help right away. because otherwise the train will be long gone. What's the net ionic equation for this? It's the same as the one above. The hydrogen ion plus the hydroxide ion forms water. I don't recommend that you just take that because I said so. You can go through all the steps and write the complete ionic equation and cross off the spectator ions and prove it to yourself. I think that's a good idea. Any questions? Acid-base titrations. Titration is a lab technique in which we take a solution of known concentration and react it with another substance where we don't know the concentration. We measure the volumes of both, and we're able to figure out the concentration of that unknown solution. And we will be doing titrations in lab. We add these solutions to each other until we get a stoichiometric ratio. So we have just enough of the first solution to completely react with the reactant of interest in the second solution. And that's called the equivalence point, where you've added the correct number of moles of substance. Knowing when you reach the equivalence point, of course, is probably the hard part of the reaction. We calculate the unknown concentration using solution stoichiometry. So how do you know when you get to the end point? Well, in acid-base titration, you've got most likely your reactant and product solutions are colorless. What we do is we add an indicator. There are a variety of organic dyes that will change color based on whether the environment they're in is acidic or basic. And so we use an indicator, and it will change color when the acidity or alkalinity of the solution changes at that equivalence point. At the equivalence point for an acid-base titration, we have the number of moles of hydrogen ion being equal to the number of moles of hydroxide ion. So here's an example, an illustration. Here we've got sodium hydroxide in a burette, which is a device that allows us to slowly and carefully, come on, Arrow. Look, the stylus is not on the iPad. Thank you. Okay, pesky Arrow. It allows us to deliver a solution and measure its volume accurately. So we're going to add the sodium hydroxide to this Erlenmeyer flask that has an acid in it. Oh, that's not necessarily sodium hydroxide, just any hydroxide, a base. And we add it to the acid, and as these hydroxide molecules are added, they combine with the hydrogen ions and form a water molecule, and they're neutralized. And so everything just kind of goes along, and we still have extra hydrogen ions, so it's an acidic solution. When we get to the point where we've added just enough of the hydroxide ions to use up all the hydrogen ions, we've reached the equivalence point where we have a stoichiometric ratio. And then we go even just a couple of little particles, part of a drop over, and the solution turns pink. And that's our signal. Hey, you just barely passed the equivalence point. Stop now. And yes, we don't hit the equivalence point exactly, but our measurements of volumes aren't exact either, and so it all works out. It's fine. Here's pictures of what that might look like. As this sodium hydroxide now is added, we see a little bit of pink forming here. Because right here, before it gets mixed, there's some extra hydroxide ion in the solution. But as soon as we swirl it, it reacts with the hydrogen ions and the pink goes away. We keep going until one drop more turns the whole thing pink and it stays pink. Phenolphthalein is the common indicator. It's got lots of pH TH, phenolphthalein. Which reminds me of that. You seen that dog?
Ethan.
Steven, yeah. He would probably like phenolphthalein. Yeah. Doing titration calculations is doing solution stoichiometry. That's all it is. Okay? We just need to think a little bit about what we're doing. Okay, so let's look at this example. We're standardizing an HCl solution. That's chemistry speak for finding the concentration of. We've got this HCl solution. We want to know what the concentration is as accurately as we can. So we put 50 milliliters of it in a flask. We add some indicator. We've got 0.1524 molar sodium hydroxide in a burette. The way a burette works is it's like a cross between a graduated cylinder and a test tube. And it's really long and skinny, but it's got markings on it. The markings start at 0 at the top and go down to 50. And the way you measure the volume is you record where the level is when you start and where it is when you finish, and then you're looking at the difference between. So this is saying the burette started out at 0.5 milliliters and ends up at 33.87. That does not mean we're putting liquid into the burette. We're asked to find the molarity of the HCl solution. Well, what's the reaction? What's the equation to describe what's going on here? We've got HCl and sodium hydroxide, right? Drawing mode, HCl and sodium hydroxide, and they're going to form water and sodium chloride. We should always look at the equation, this acid-base neutralization equation, because if we have a polyprotic acid or if we have a base with more than one hydroxide, the stoichiometry is not always 1-to-1. We look at this one, and here it is, 1 HCl for every 1 sodium hydroxide. So this is telling us, and we can use this to organize ourselves here. We've got 50 milliliters of HCl, and we've got 1,524 moles per liter of the sodium hydroxide. Do we know the volume of sodium hydroxide that was added? Yeah, we have to figure it out a little bit. But we take the 33.87 milliliters and we subtract 0.55 milliliters. And I think that comes out to 33.32. So 33.32 milliliters. So that's pulling information out of that forest of words and setting it aside so we can look at it easier. Find the molarity. What are the units on molarity? Moles per liter. So to find the molarity of the HCl solution, we need the number of moles and we need the volume in liters, right? Do we know anything about the volume? Right here, 50 milliliters, right? We could convert that to liters. So 50 milliliters, this is the thorough way, milliliters on the bottom, liters on top, milli means 10 to the minus 3. The shortcut way, and we deal with milli and kilo a lot. So you take this decimal point and you move it over 3 places. So it's 0.0500 liters. The trick there, of course, is remembering which way to move the decimal point. So that's where you put on your thinking cap and you turn on your common sense. And you think, okay, we've used those 10 mil graduated cylinders. How big is a milliliter? It's little, right? Think of half of a 2-liter bottle of soda. That's 1 liter, right? Is that bigger or smaller than a milliliter? It's bigger, duh. Well, could 50 milliliters be 50,000 liters? No, that's moving the decimal point in the wrong direction. Okay? So you are very welcome to do the shortcut, just move the decimal point over. Just make sure you can do it in the right direction. If you just, some people just have a mental block on that and they're just always going off in the wrong direction, then write it out. Get it right, okay? So anyway, there's the volume. What else do we need? We need moles. This is where the stoichiometry comes in. So what we're doing here is we've got a volume of sodium hydroxide that we can convert to moles of sodium hydroxide that we can convert to moles of HCl. Now normally we continue on, right? But we just need moles. So this is our mantra, grams to moles to moles to gram. But we're making a couple tweaks. We're going to start with volume to moles, and we're going to stop. Okay? So volume of sodium hydroxide. Well, 33.32 milliliters. Well, this is our conversion factor, the concentration, that's in liters. So let's convert this to liters. This is the small unit. This needs to be the big number, so we need to move the decimal point that way so that we have a small number, 0.03332 liters. So there's our volume of sodium hydroxide. We're going to convert to moles of sodium hydroxide. Liters will be on the bottom. Next is moles of HCl and moles of NaOH on the bottom. Ooh, that got tiny. Sorry about that. Moles to moles comes from the equation. In this case, it's 1 to 1. It's not always. That's why we should include the term. This is the concentration that we are given, 0.1524. 0.1524. 0.03332 times 0.1524 times 1 over 1 0.005077968.
Where'd you get the 0.03332?
Where did I get this? That's a good question. That is this volume converted to liters by moving the decimal point over 3 places. Okay, so this is moles of HCl. Yeah, that's way more sig figs than we need, but that's okay. That is this number here. That's the moles. I've got that in my calculator. What's the volume? Let's use a different color. This is the volume. That's down here. I'm going to take this number that's still in my calculator. I'm going to divide by 0.0500. And I'm going to come up with, calculator says, 0.010155936 moles per liter. How many sig figs should that have?
4, 2, no, 3, 4.
3. So we have to go back and see, where did all this come from? Right? It's like a detective mystery or something. Because you can't just look and say, oh, well, this has 2 sig figs, so my answer is 2 sig figs. Because this is subtracting. When we do this subtraction, we still have 4 significant figures. So that volume had 4. That's this volume down here, still 4. That's got 4. But this guy has 3. He's limiting it. So we're going to use 3 sig figs in our final answer, 0.102 molar. That is the concentration of the HCl. And we write that on the bottle, and people looking at it understand that there's some uncertainty in this thousandths place. We don't want to write all of this on there because that would imply that we know the concentration much more closely than we do. But we also don't want to say, oh, it's 0.1, because that means between nothing and 0.2. That's a huge range. Questions? Is there an extra slide? There is, because I took the one with the 2 equations and I split it into 2. So there are some small differences, I'm sorry. Yeah. Oh, good grief. It's a chapter that won't end. We're out of time, so I'll see you tomorrow.